Hi, everyone. Okay, this is part two of the matrix commands for homework 7. Part one, we talked about this just the spectral decomposition, the type of stuff, just how to think of multiplying by symmetric matrix as three multiplications, a rotation, a stretch, and a rotation back. Now we're going to look at these best K-rank approximations to a symmetric matrix, as in this problem 4, and we'll also do a Cholesky decomposition as in problem 5. That's part 2. Okay, so just these two things. I'm going to try to keep the video short, like around 15 minutes, and upload it. Okay, so I've learned that to share, I do have to stop and reshare my different screens if I want to have stuff working. So let me stop sharing and we will do the first piece first. So I'm going to share my this one, my R screen here. Okay. Okay, you with me? Okay, yes. So let's have some symmetric matrix like that one down there. That's 5 by 5. I don't need to make it 5 by 5, but I want a symmetric matrix. So one way to quickly build a symmetric matrix, if you're making these problems up, is to multiply by ATA, where A has um, independent columns. So let me do it this way. I'm going to make a matrix A equals C bind, and let's just make it a let's make it 4 by 4. So I'm going to make it 4 columns. So I'm going to have C, and now I can just put any kind of garbage I want in here. Yeah, why not? And I'll just make this garbage have like 6 entries. It doesn't even matter. C minus 12, 0, 1, 1, 13. I just got to make sure I don't. You could even have it be like pi and exp1. You could put whatever you want here. 3 minus 4 and 0. Okay, I got 3. One more, right? I'm totally randomly just picking things here now to put in here. You don't have to worry about this. Uh, 0, 5. Let's try this. And it worked. So there's A. Looks pretty crazy, but now to make S, I'm just going to go S equals TA times A times A. S is symmetric. Notice how it's symmetric, right? Oh, now did I get lucky there? No. I just figured if I took 4 columns of size 6 each, 4 vectors in R6, that they would not be dependent. It'd be pretty strange if I guessed and one of them was a linear combination of the other. So I had independent columns, and remember, in this case, ATA will give you a symmetric matrix. Okay, and I think it's positive. Definite 2, yes, it should be positive definite 2. You can do that proof. You can see it in the book. We didn't do it, but you will be able to see it. Now I could clean this up and round it. Why don't I do that just to make it a little more palatable? Let's say S equals round S. Let's just make it integer, okay? A little easier to read. And you see S there now. It's symmetric, right? Okay, so let's use that trick. So I'm on problem 4 now, where we're going to find, let's say, the best rank 2 matrix. But first, let's do the eigenvalue decomposition, because we want to think about the size of the eigenvalues when we do this. This is the important part, the relative size of the eigenvalues. So let's go A equals, you can call it whatever you want, eigen S, and A $sign values will give me the eigenvalues. Okay, look, pretty good. The first three are really good. So you can see if I take the first three components and take the best rank 3 matrix to this, I'm gonna have something extremely close. The best rank 2 one, okay, well, not as close, right? Because you're still leaving out about 10% of it here. Um, but you will get something somewhat close. So I think the best 2 rank and 3 rank are the interesting ones for this. So sort of like, I think the problem. Um, okay, so let's just do this. So I want S1 then equals, let's say the best 1 rank, rank 1 approximation to S. And here I'm just going to take lambda 1, right? So A $ values. You could pick something easier to call this. And here I just want 1 and just a regular times. And now I want A $ vectors. And here I want all the rows, but just the first column. And now I want to multiply by Q1 transpose. Okay, so by the way, if this is not easy to see, I mean, you could enable like name these lambda 1, Q1. This is Q1 here and Q2. Maybe I'll do that when we do the next one. Okay, and then the next one would be A $ vectors, but transpose, right? So transpose A $ vectors. First one again. Okay, does it look right? The A, so lambda 1, Q1, Q1T, looks right. Let's look at round S1 and look at S. So I started with S and I'm here now and it looks not bad, right? You can see, look, this one's exactly right. This one's exactly right. And you can see the shape is roughly correct. But it's still quite a bit off. We kind of expected that. Let's add the next one. So I want to put 2 in now. And I'm going to call this, let's call this S2, and then we'll overwrite it. Okay, and let's call S2 now equal to S1 plus S2, the best rank 2 thing. Now let's look at S. It's the thing we're trying to approximate with this S2. Let's look at round S2 and S. Okay, so this is the approximation to this. You can see it's getting closer. Okay, look, minus 80. Look at this row, the second row, 41, 49, minus 84, minus 82, 315, 316. Okay, so it looks pretty good. Now, if I take the next one, it's going to be super close, but it's already getting there. Let's do one more. Okay, and S2 was the best 2 rank one, so let's make S3 the best 3 rank one. We'll say S3 equals S2 plus S3. And let's look at S, and let's look at S3. This should be close. Sorry, let's look at S. Let's look at round S3. Look at that. First row is right when it's rounded, no decimals. Second row is right. Third row is right. Fourth row is right. Okay, pretty good, right? Just leaving out that last component there, but we saw the relative size of these A $ values. Only, 0.18 here compared to like 1,300. So less than 0.1% of the mass, and you get the full matrix back with this. Well, when it's rounded, it's not going to be perfect. If you don't round it, if we go like just S3 and say round it to 2, it's not going to be perfect, I bet. Okay, you see, First row is perfect. Second row, you got these little errors here and here. Okay, rushing to get through this to do the last thing, we want to talk about the Cholesky decomposition. So if you have a symmetric positive definite matrix S, like we do, and let's just do it right for this one. The way to find the Cholesky for S is, here, we'll do it here. So that's it, okay? Notice that is not the original A that we started with. We had longer rows that we built S out of. That's fine, longer columns. Columns in R6. So what is the Cholesky matrix S? Well, I can take S and do an LDU decomposition. So this is equal to, let's just write it as a comment here. Hashtag for comments in R, LDU, right? Equals S. But because it's symmetric, this is L transpose here, right? But because it's positive definite, I could write D as square root D times square root D. And not only that, it doesn't matter if I take the transpose of this because, why? Because it's a diagonal matrix. So that should be true too. These are just comments. So even if I did write something incorrect, it would not show up. Okay. So, but this looks correct to me. Now, the last thing, I can think of that whole thing as A here. Okay, and if I take the transpose of A, I get, these transposes become undone. So let's write this now. A equals this. Okay, A is equal to that. And then A transpose then should be equal to this. Because it goes, the order changes, and then I take the transpose of each. And so I get that. So now I have S equals AT times A, where A is equal to this. So the whole thing with Cholesky comes down to just finding LDU and then writing the Cholesky matrix is just equal to, I don't want to do that, right? Yeah, and then the Cholesky matrix is just equal to L. Sorry, the Cholesky matrix is this one, is just equal to the transpose of D times the transpose of L. The one on the right, the upper triangular one. Here it is. Okay, so let's just do this manually. So to do the LDU, you need the command LU decomposition. It is in the package. I think it's in the package Pragma or Matrix Calc, one of the two that was in the part 1 video. So let's just do it. So I'm going to type LU decomposition. I don't know why I'm talking like that. S. And I get that. Okay. And let's save those. So I'm going to call this like B equals LU decomposition S. Okay. So I have my lower, so I'm almost there. I just need my diagonal matrix here. So how do I get a diagonal matrix from this? From you, I basically want to just get rid of these off diagonal entries and I'll have my diagonal matrix. So let's let D equal U for now. Might as well. Uh-oh. Oh, right. I didn't. B. Never panic, right? So D looks good, but I'm going to get the off diagonal ones off there. I'm just going to get rid of them by setting them to 0. And I'm going to take the square root of D too. Okay, so D, let's say D. So this shows you some other things you can do. You can say D, let's see, D1 Now I want to go from 2 to 4 equal to 0. That worked. And the 2 from 3 to 4 is 0. And the 3, and let's look at D. Okay, that's D. And now we want the square root of D to get the Cholesky matrix. So our last thing is our Cholesky A. A is, what did we say it was? Square root of D, square root D, or the transpose to be technically true, but it doesn't really matter, of the square root of D times the transpose of L. So let's just say, let's just do it. So let's go transpose D times transpose L. I got to take the square root here. Okay, so let's do it. So we get, I don't need to take the transpose, so I'm not going to because it's just diagonal. So square root D times T B $L. Let's call it A, new A. And let's check against the Cholesky thing that we had. So what do? We had Cholesky. Did we call? Yep. So there's the Cholesky one and A, same thing. Okay, so that's how you can find the Cholesky decomposition by hand. The other side of the Cholesky decomposition is the it's the flip of this. The diagonal's the same, but everything else is it's the transpose of this. So basically, right, if I have A here and if I go now ATA, I should get back S, right? So let's check TA times A equals S. So there's my A, TA, let's check. TA looks good. So now let's go TA times A, boom, S. So it's like the square root of a matrix. If you ever wanted a square root of a matrix, this is what you want, the Cholesky. Well, so it's usually what you want. It's one of the things you might want, to put it that way. All right, so we did these two. This is part 2 of the 2 videos on our commands for homework 7.